Okay. So in last lecture, we have completed the design of a circular water tank resting on ground when it is a rigid base using I-sport method of design. Approximate method, I-sport method, both methods I was covered in last previous lectures. Okay. So now I am going to tell you how to design the rectangular water tank. It is resting on ground. How to design the rectangular water tank? It is resting on ground and using approximate method of design, rigid base. Okay. So there is no flexible base rectangular tank in our syllabus. Okay. So if the rectangular tank, you have to consider that tank is always rigid base. Always rigid base. If the base is rigid, so we know that if the base is rigid, you have to design the wall for two forces. One is the hook tension and another is the bending moment developed at the base due to fixity. But in a rectangular water tank, you have to consider one more force, that is the hook tension is there as well as base bending moment is there. But you have to consider one more new force, that is the lateral bending moment developed due to the hoop pressure. That you have to consider. Lateral bending moment developed due to the hoop pressure, that you have to consider for design of water tank. Okay. So initially I will tell you some theoretical part of a water tank. So in rectangular water tank, you have to consider the two aspect ratio. Okay. One is in that first one. So let it is the rectangular water tank. That it is a rectangular water tank. I am drawing the plan for that. I am drawing the plan for that. Okay. Okay. So this is the capital L. Okay. And this is the small l. This is small l. So this is a longer span and this is a shorter span, as we are considered in a design of a slab like that. Okay. So we have to find out the aspect ratio. When L upon L ratio is less than 2, when L upon L ratio is less than 2, then what you have to consider? You have to design each wall spanning between two adjacent walls. Okay. Design, I will write here. Design each wall. Design each wall spanning between. Design each wall spanning between two adjacent walls. What is the meaning of this sentence? That means this wall is spanning between these two walls and this long wall is spanning between these two short walls. That you have to consider and design the tank. Okay. Now second aspect ratio, what you have to consider? The second aspect ratio. Now look the shape of the tank. The long dimension is higher as compared to the shorter dimension. Okay. So this is the capital L. Okay. And this is the small l for the tank. So both are the plans. This is plan. Okay. This is again plan. Now what is the aspect ratio? Now here L upon L ratio is more than 2. Obviously L upon L ratio is more than 2. So what is the situation here? So this short wall is spanning between these two long walls. Okay. So short wall spanning between two long walls. Okay. This short wall spanning between two long walls, but this long wall is not spanning between the short wall, because the long wall having more length as compared to the short wall. Okay, so short wall spanning between two long wall, and long wall acting as a separate cantilever wall. Long wall acting as separate cantilever wall. Separate cantilever wall, that you have to consider. Okay, so what you have to consider? There are two aspect ratio. One is L upon L ratio is less than 2. So what you have to consider the design criteria. Each wall is spanning between two adjacent walls. Like this you have to design. And when L by L ratio is more than 2, so what criteria you have to consider? Short wall is spanning between two long walls, and long wall is acting as a separate cantilever wall. Like this you have to design the each wall. Like this you have to design the each wall. Okay, isn't it? Now I will tell you how the bending behavior of each wall when the water pressure is applied on the wall. Okay, let's consider this tank. So this is a rectangular tank. So this is the plan of a rectangular tank. Okay, so when water pressure is acting on this wall, so this wall get bent like this. This wall get bent like this in plan, as well as when the water pressure is acting on the short wall, also this wall is bent in this direction. As well as this joint is always treated as a rigid joint. This joint is always treated as a rigid joint. Okay, so this wall is now going to subject two bending moments laterally in plan. One bending moment is developed due to the pressure of water in plan laterally. Okay, so this bending moment is called mid-span bending moment. Mid-span bending moment, and due to rigid joint at a corner, so this section is subjected to the corner bending moment. Corner moment. Okay. So what exactly you have to consider? You have to design each wall for two bending moments. One is mid-span bending moment, another is the corner bending moment. So I will show you exactly how the bending behavior of the wall using this sample of this box. So let's consider this is the one of a rectangular water tank. Okay, so this is the short side, short wall, this is a long wall. Okay, so this is the short wall and this is the long wall. Okay, so when the water pressure is going to act on this wall, look the bending behavior of the wall. If the water pressure is acting on this wall, the bending behavior of the wall is like this. Okay, and when the water pressure is acting on the short wall, the bending behavior of a wall is like this. That means each wall, this is long wall, short wall. Each wall you have to design for two bending moments. One is the mid-span bending moment, one is the corner bending moment, and that both bending moments are developed due to the water pressure. Laterally. That means in plan. But base bending moment is also there. Okay, so that base bending moment is developed longitudinally. That means you have to design the wall. For you have to design each wall for two bending moments. One is bending moment at midspan, one is bending moment at corner, and that both bending moments are developed due to the water pressure. Okay, isn't it? Now I want to tell you how exactly the rectangular water tank is to be designed. Okay, so generally first you have to provide the thickness, then you have to design each wall in plan. Each wall in plan like this. Each wall in plan. You have to design one wall at midspan, one wall at corner. So, for example, if the rectangular water tank you have to consider, you have to design the long wall at midspan. You have to design the long wall at corner. Same thing you have to do. Same thing you have to do. You have to design the short wall in midspan, short wall in corner. That's it. And you have to provide the reinforcement. You have to provide the reinforcement. You have to provide the reinforcement horizontally like this. You have to provide the reinforcement horizontally. That means you have to provide the reinforcement horizontally like this. Okay, to avoid the lateral bending of the wall. To avoid the lateral bending of the wall, isn't it? Now I will tell you exactly how to design the rectangular water tank. Okay. So initially first you have to check that L upon L ratio. Okay. So these steps are related to when L upon L ratio is less than 2. Okay. So whatever I am going to tell you now, that steps are related to when L upon L ratio is less than 2. When L upon L ratio is less than 2, you must consider one criteria, and that criteria is each wall is designed spanning between two adjacent walls. That means this wall is spanning between these two walls, and this long wall is spanning between these two short walls. Okay. So what are the steps? I will tell you. The step number 1. The step number 1 is provide. Step number 1 is provide thickness of wall. In step 1, you have to provide the thickness of wall directly. Thickness of wall is equal to 30H. 30H plus 50, we know this formula. So first you have to provide the thickness of wall, and thickness of wall is 30H plus 50. 30H plus 50. So this is the thickness of wall. Okay, thickness of wall. Now you have to start the design of a wall. I will tell you, already I have told you that each wall is laterally designed. Each wall is laterally designed. That means you have to design the wall in plant bending moment. So if you want to design this wall, long wall, that it is a long wall. So this due to the water pressure, this wall is bent in this direction. So this wall is bent like this. This wall is bent like this in plan. Okay. So there is development of a bending moment at center. There is a development of bending moment at center. So what you have to design? You have to design first this long wall. You have to design first this long wall for mid span. At mid span, you have to design the wall at two locations. One is at mid span, one is at corner. Now I will tell you how to design the wall in mid span. So design the wall at mid span. How to design the wall at mid span? How to design the wall at mid span? So what you have to do? You have to follow 4 important steps. One is you first have to find out the hoop tension at that location. Second, you have to find out the bending moment developed due to hoop tension at that location. I will again repeat it instead. What is exactly the design of a wall in mid-span? In that you have to follow four main steps. One is, first you have to find out the hoop tension at that location. Second, you have to find out the bending moment developed due to hoop tension laterally, okay, in plan. And third, you have to consider the net effect of these both. That means you have to find out the net bending moment. You have to find out the net bending moment. And fourth step, you have to provide the steel for that net bending moment horizontally. That's it. That's four steps you have to follow. The design of the wall in each location, you have to consider the four main steps. One is find out the hoop tension at that location. Second is find out the bending moment developed due to hoop tension at that location. Third, net bending moment. Fourth, steel for that bending moment. That's it. So first you have to find out find out the hoop tension. Find out the hoop tension at that location. Hoop tension at that location. So I am designing the wall first laterally. Then for that lateral bending moment, I am going to provide the horizontal steel, and finally I will provide the vertical steel. Okay. Now first to find out the hoop tension at that location. So this is step number 1. Hoop tension T is equal to gamma W into H minus H dash. Look here. Gamma W into H minus H dash. This formula is already we have used in a rigid base approximate circular rigid base approximate method. Okay, in circular water tank. So gamma W into H minus H dash. So I am going to design a long wall. So I am going to design now long wall. Okay. So long wall design at mid-span section, you have to follow 4 steps. Okay. Hoop tension T is equal to gamma W into H minus H dash. On this long wall, the water pressure is coming in this direction. On this long wall, the water pressure coming in this direction. That means you have to consider the small l here. You have to consider here small l divided by 2, isn't it? Divided by 2. This is the formula for the hoop tension. Now step 2. Step 2, bending moment. Bending moment due to hoop tension. Bending moment due to hoop tension. Bending moment developed due to hoop tension. That is bending moment M. Bending moment developed due to hoop tension. That is M. So now, what is the formula? Formula is gamma W into H minus H dash. H minus H dash into. So this bending moment is related to mid-span. Okay. So what we have to consider gamma W into H minus H dash into L square. So now you have to consider the length of that long wall. Now you have to consider the length of the long wall. It is capital L. Now you have to put here capital L. So because this bending moment is developed due to the along that length. Okay, so you have to consider the capital L. Again you have to consider the effective square. What is the formula? Gamma W into H minus H dash into L effective square divided by 16. 1 upon 16 is the coefficient at mid-span. Okay. Now step number 3, net bending moment. Step number 3, net bending moment, isn't it? Step number 3, net bending moment. So how it is calculated? Net bending moment M net is equal to M minus T into X is the formula. So we have to consider the effect of this both, the hoop tension as well as bending moment. So what is the net bending moment? It is M net is equal to M minus T into X. M is this bending moment, T is the hoop tension, and this is the effect of the both forces. This is the effect of the both forces. M minus X. I will tell you exactly what is the X. Okay. So if you consider the wall like this, so this is the total thickness provided for that wall. And so this is the center of this wall. And the reinforcement provided at this wall like this, because because this bending moment is developed laterally. This bending moment developed laterally. So you have to provide the reinforcement horizontally in this direction, horizontally in this direction. So this steel is for the to avoid the bending moment, lateral bending moment. Okay. So now you have to consider. So this is your effective cover. This is your effective cover. Now what is X? So this distance is nothing but X. This distance is nothing but X. This distance is nothing but X. That means both forces, bending moment and hook tension, generating the moment at the center of this wall. So that this distance is important. How it is calculated? So we know that this total is, this is nothing but T by 2. This is nothing but T by 2. Okay. So center of this T by 2, center of this T by 2. So what is X? So X is equal to T by 2 minus effective cover. Okay. So this is the formula. So this is T by 2 minus effective cover. You will get the X. What is the meaning of X? X is the distance from the CJ of this reinforcement up to the center of the wall. So this is the X. Okay. So step number 1, step number 2, step number 3 I was covered. Now what is step number 4? Step number 4, provide the steel. Provide horizontal steel. Provide horizontal steel, isn't it? So what is the formula? So AST is equal to M net. You have to provide the horizontal steel for the net bending moment. M net is equal to sigma ST into J into D. So these are the main 4 steps to follow to design the wall at each location. Okay. So these are the steps. These are the steps that we have to consider. These are the steps that we have to consider for design of a wall in mid span. Okay. First, find out the hook tension, find out the bending moment due to hook tension, the net bending moment, and finally the first step is the steel provided horizontally, because this bending moment is lateral bending moment. Now same steps you have to follow. Same steps you have to follow for design of a wall at corner. Same steps you have to follow for design of a wall at corner. Okay. So now you have to follow the same steps. Now I will show it here. Okay. Design of a long wall at corner. Okay. Design of long wall at corner. Okay. Design of a long wall at corner. You have to follow same steps. First step, hook tension. First step, hook tension. T is equal to same formula. Okay. Gamma W into H minus H dash into small l divided by 2. Isn't it? Okay. Then step 2, I will write here. Step 2, the bending moment due to hook tension. So bending moment due to hook tension is having formula same. Gamma W into H minus H dash, because this bending moment again related to the long wall. So this is L effective square, but now the coefficient is different. The coefficient at mid span is 1 by 16 and coefficient at corner is 1 by 12. Only this change is there. Now what is step number 3? Step number 3 is the M net. Net bending moment is M minus Tx. And fourth step is steel. AST is equal to M net divided by sigma ST JD. These 4 steps you have to follow for design the wall at corner, and these same steps to follow for design the wall at mid. So this is the design of a long wall. This is the design of a long wall at mid and at corner. So what you have to do? First step, you have to provide the thickness. Then you start to design the wall at 2 locations. First you design the long wall at mid, long wall at corner. Okay. For design the long wall at mid, you have to consider the bending moment coefficient. Okay, at mid span is 1 by 16. All other steps are same. And bending moment at corner, to consider the coefficient 1 by 12. This is the only difference. This is the only difference you have to consider. Okay, so this is the design of a long wall laterally in plan at two locations, at mid span and at corner. Now same step you have to follow. And design the short wall at mid and corner. Design a short wall at mid and corner using same steps. I will tell you. Now I will rub this. Okay. Now design of a short wall. Okay. So due to the water pressure at short wall, this wall get bent like this. Okay. So again design the wall at mid. Okay. So design of wall at mid corner. At mid span. Design of wall at mid span. Okay, design the wall at mid span. So what do you follow? You have to follow that 4 steps. Okay. Step number 1, hook tension. T. Okay. Same formula. Gamma W into H minus H dash. Now you are going to design a short wall. So on short wall, the water pressure coming in this direction. So you consider capital L divided by 2. So this is the formula, isn't it? Then second step, bending moment. At mid span. So what is the formula? M is equal to gamma W into H minus H dash. Now you are going to consider the bending moment at mid-span along that wall. That means you have to consider here L effective square. Now you have to consider a small l because we are going to design the short wall. At mid-span coefficient is 16. We know that mid-span coefficient is 16. Third step, net bending moment. What is the formula? M net is, we know the formula, M minus Tx. And fourth step is steel horizontal steel, that is AST is equal to M net divided by sigma ST GD. M net divided by sigma ST GD. So these same steps you have to follow. Now what you have to do? Now you have to design the short wall at corner. Now I am only replacing this design of a short wall at corner like this. Design of a short wall at corner. Same 4 steps to follow. Now design of short wall at corner. Hook tension having same formula. Bending moment same formula, but the coefficient different. You have to only change this 1 by 12. And all other things are same. So this is the design procedure of a rectangular water tank laterally. That means for horizontal steel. Now I will tell you how to provide the vertical steel. So provide vertical steel for base bending moment. Okay, so first we'll find out the base bending moment. Base bending moment is bending moment M is equal to gamma W into H cube by 6. So this is the base bending moment developed due to the rigidity at base. Okay, and provide vertical steel. and provide vertical steel. You know that AC is equal to base bending moment divided by sigma STG. Okay, for calculating of steel, you have to follow the same formula at any location for under reinforced section. And finally design base slab. Finally design base slab as usual. Provide sufficient thickness and provide this minimum steel. That's it. So this is the design steps of the rectangular water tank. So I will repeat it. First, you have to provide the thickness. Second, you have to design the long wall at mid-span section. For mid-span section, you have to follow 4 steps. One is hook tension at that location. Second is bending moment developed due to the hook pressure at that location. Net bending moment and steel horizontal. Enough. Okay. Second, you have to design the same wall at corner. Same steps. First, hook tension. Second, bending moment at that location. Net bending moment, steel. This is the design of a one wall. Same steps you have to follow for design of another wall. Design of a short wall at mid and corner using these 4 steps. And provide the vertical steel for base bending moment. Gamma W is given by 6. And design the base slab like this. So now I want to tell you how the reinforcement is provided. How the reinforcement is provided. How the reinforcement is provided. For that, I want to sketch the one small 3D view of the tank. One small 3D view of the tank. Okay, isn't it? I will try it. Okay, so this is the wall. This is the tank. So these are the base slab. Now I want to show the 3D view. Okay, so I don't want to plot it a total 3D, only up to the reinforcement detail I will show it. Okay. Isn't it? So this is the wall, rectangular tank. Okay, 3D. So horizontal steel, look here. The horizontal steel provided like this. One is at that face, one is in this face, one in this face, one in this face like this, one in this face, one at this face, one in this face. So this horizontal steel is provided for lateral bending moment. For lateral bending moment, that means that net bending moment. Okay. So this steel is provided for net bending. Okay. Same thing you have to do here. Same thing you have to do here. And you have to provide. The vertical steel. You have to provide the vertical steel like this. In this face, another this face. In this face, another in this face. Okay. In this face, one is space. In this face. So this vertical steel is provided for that base bending moment. This vertical steel is provided for base bending moment, which is developed due to fixity at base. It is developed due to fixity at base. So this, like this, you have to show the reinforcement. Like this, you have to show the reinforcement details, isn't it?